Dear student, let us begin the lectures on machine design part 1. This is lecture number 21 and the topic is shaft coupling. This is the concluding lecture on the same topic. So, before going to the subject proper today, let us recapitulate little bit what we have learned in the last lecture. We talked about the couplings. Now, couplings are used to connect two shafts for relatively long time. And there are primarily two types of couplings. One is rigid coupling. As the name suggests, the coupling is made of a rigid material. There are few kinds of rigid couplings which we discussed, namely flange coupling, which is the common type of coupling, then sleeve or muff coupling, then we discussed clamp coupling, and then compression couplings. But towards the end of the lecture, we mentioned that there are few disadvantages of the rigid coupling. So, we are going to start from that point today. Let us look at some of the disadvantages of rigid coupling now. First, no provision for shaft misalignment. Now, I want to emphasize here that shaft misalignment, there may be few kinds of shaft misalignment. One may be here one shaft, another shaft here. So, there is a parallel offset, maybe shaft one here, another there. So, this is angular offset or angular misalignment, and there may be a combination of both, that is there may be an offset and angular mismatch. So, these are the three basic types of misalignments, and the rigid couplings are incapable of providing for these misalignments. Then large bending stress develops. Whenever there is misalignment, if you want to bring the shafts together, then a large bending stress is developed, and that is detrimental, because when the shaft runs, then it leads to the fatigue loading, large fatigue loading also. Again, if we attach the rigid coupling where there is a large bending moment due to various other reasons, then also the bending moment is quite detrimental. The last point, and which is very important, that is shock and impact loads get transmitted. So, the rigid couplings are not capable of providing any cushion to the shock or impact loads. Now, the main point of departure today will be the flexible couplings. Now, these above advantages can be reduced to some extent. You will see after today's lectures that what are the extents by flexible couplings. So, let us now come to the flexible coupling. Now, there are few types of flexible couplings. One is the couplings with kinematic flexibility. That is, the flexible members or the flexibility of the coupling is made by having some kinematic pair inserted between. So, depending upon the kinematic pairs, the couplings may have different kinds of flexibility. One type is cross sliding coupling. Here we use two prismatic pairs. Universal joint, which uses spherical or special mechanism. Gear or tooth coupling, this is again a higher pair mechanism, and chain coupling, which consists of large number of revolute pairs. So, it leads to a large flexibility of the coupling. Then couplings may be of resilient members. Now, here the flexibility is brought in by with the help of the members which have their inherent flexibility. Now, the most often used flexible members are elastomers, that is they may be rubber or some polymer or some synthetics. Now, they again work in basically two or three ways. One is shear and another is compression. Again, sometimes we use metallic membranes. Now, metal as such is very rigid, but whenever we make a thin plate of metal, that is metallic membrane, then we can get a large amount of flexibility. So, that all of you must know. Then flexible metallic membranes could be used in various ways. It may be used as a spring, then disc and diaphragm. So, these are the basic types of flexible couplings which we are going to discuss now. The first comes the Oldham coupling. Here you see, this is again, this name is not new to you, because while learning kinematics you must have come across this name. This is a mechanism which has three pair, the 4 joints, which is one is revolute pair and 2 prismatic pairs and 1 revolute pair. Let us see how they are attached. So this is one part of the shaft. This part is connected to one shaft. This part is connected to other shaft. And here there is one floating member. And on this floating member, we have 2 tongues which are made 90-degree apart. Similarly, here we have 2 slots which meet or mate the these 2 tongues. Now you see, here we have revolute pair. There in this locations we have a prismatic pair, and there we have another prismatic pair, and again this is revolute pair. And so you might have learned that the inversion, kinematic inversions of these mechanisms may be elliptic trommel or hand operated pump, etc. Now Oldham coupling, how does it operate? How does it add to flexibility? You see, whenever there is a little offset from this distance, now here one point is that Oldham couplings work when there is a parallel offset. It does not take much care of the angular misalignment, but whenever a parallel offset is there, so this coupling, that is this part, gets engaged, but it can slide over this slot. So therefore the slot, the length of engagement gets changed, but it transfers torque from one shaft to the other shaft. Then a variant of Oldham is cross sliding coupling is known as American flexible coupling, which again works on the similar principle. Here one shaft, one part is shown here. It is, there is one recess here, which the cross section, or from this side it looks like that. Similarly, there will be another coupling, another half, which will have recess here. So inside there is a square hollow, and this is filled by this kind of slider. So this is again American, this is again flexible coupling based on the cross sliding movement. This a hollow is made in order to reduce the weight, and this part is made by elastomers or some kind of synthetics which reduces the weight. Now these are about the Oldham coupling. Now let us look at the design principles of Oldham coupling. You see, the torque gets transmitted by means of this tongues. So it is very important to design this tongues. So the strength will be taken by this tongues itself. Now we are going to see how a designer can approach this problem. Now coming to the design criteria of Oldham coupling, let me draw the side view of a shaft. So this is the coupling, and the other part of the coupling, or other part of the coupling, gets shifted by some amount, let us say E. This distance is E. Then the slider, which is there, this is the slider, that is the floating member. Now this portion is only subjected to pressure. If the diameter, original diameter is D, then this is D minus E, what you can verify very easily. Then you see, when I draw the this is again the slider, and this length is d minus e. This is the end view of it, so which has width h say, and this length is d minus e. Therefore, the force will act on it. Now, it is difficult to find out the exact distribution of the force, but what we can assume that the force is now triangularly distributed. That is, the distribution is somewhat like this. So, it goes from 0 to a maximum p. Now, again what will be the p? This p again depends on the material. So, it depends exactly, p must be less than equal to sigma bearing, that is the bearing stress must be p must be lesser than this bearing stress. So, once this is done, then we can find out, we can replace this entire loading by a torque. And what will be this torque? This torque is, now you see here the equivalent load is F, and there F is equal to half times P, the area of this triangle, PH is the force per unit length, times d minus E by 2. And then we have the distance, this distance is 2 of this distance, which is equal to, so d will be equal to 2 of, this is 2/3 of d minus E by 2. Therefore, the torque will be, now if you do these calculations, then the torque becomes equal to F times d, which is equal to 1/6, you will see P d minus E whole square times H. So, from which we can find out that the maximum pressure P will be equal to 6T by d minus E square times H. If E is much smaller than d, then this is approximately equal to d square H. Now, you know this torque, the capacity of the coupling, and so you can find out this P. Now, P must be lesser than sigma B, therefore, you can design what will be this H. So, this thickness could be designed that way. Well, now this is for the case when there is no clearance, but invariably there will be some manufacturing tolerance, etc. So, there will be some clearance. Let us see what happens for the clearance case. So, whenever we have some clearance, then we see that if this is the part of the, this one is the part, and here suppose there is a clearance, the slot. So, now the effective length will be much reduced. So, if the pressure acts not over the entire surface, but over a small surface. So, if I draw it elaborately or much longer, then it becomes something like this. So, this length, there will be a gap between the pressure length and this, again this length is of course different. So, therefore, we have to get some corrections, and usually normal procedure is to take the P to be 8 times T divided by this capital D square So, this is from this we can get the dimensions or get check for the stresses. Now this is about the old design of Oldham coupling. Now let us see what are the problems with the Oldham coupling. You see, whenever there is an offset of E, then this floating member, it makes a revolution of again the floating member, the center of the floating member makes a circle with radius E, and because it rotates with radius E and it has some mass, so therefore some centrifugal force is developed, and when a centrifugal force is developed in one member, then it leads to bending stress in the shaft. That you must all verify. You draw a diagram and it will be immediately clear. But this bending stress is again fluctuating, so again it leads to fatigue stress, that is the variable loading, and the shaft may be subjected to the high fluctuating stress, which may lead to failure. So it's always advisable to reduce the weight of this floating member, because then the bending stress will be then small. Another defect is that there is always a rubbing taking place here. Okay, this rubbing again causes wear and tear. So a high wear and tear takes place, and with wear and tear, of course, comes the frictional loss. Therefore the efficiency goes down. So there are few advantages, that is bending stress may be developed, then the wear and tear may takes place, or the efficiency may go down because of the high frictional torque, the frictional resistance. Now this is about the Oldham coupling. Now let us come to another kind of coupling, which is known as universal joint. Let me describe what is known as universal joint. Here you see, universal joint was okay, this is also sometimes called Hooke's joint. It was for this was proposed by Hooke's, but the entire analysis was done by Cardan much later. So sometimes you can hear the name Cardan joint also. So the basic analysis was done by Cardan also, although it was made for the first time by Robert Hooke. Now what are the basic principles here? Now this is the part of the shaft. This is a part of the shaft, and here we have well, this is connected to another shaft. This is shaft 1, this is shaft 2. Okay. Now this is connected by means of what is known as the Cardan pair or some kind of pin. Now that pin looks little odd. So this is not a single pin. So pin sometimes looks like this. Now this part, this shaft is connected to this pin. So the shaft 1 is connected to this pin, and shaft 2 is connected to that pin, that part of the pin. So therefore when the shaft 1 rotates, then you see the shaft 2 will be rotated. Now it can take care of some angular misalignment. So we will see in the in few minutes that how does it take care of this angular misalignment, but it can take care angular misalignment. Then this the amount of angular misalignment which can be taken care may be increased if you joint two such universal joints together. So we make double joint. So how, say this is the first shaft, let us say. Now the second shaft is somewhere here. So this is alpha 1, which the maximum angle can be taken care, and usually by one Hooke's joint you can take care of up to 45-degree angles. But then if we can add one third member into that, then we can take care of alpha 2. So the total may be alpha 1 plus alpha 2, which is the total angular misalignment which can be taken care of. What you see here is nothing but two such joints. Okay, here one joint, you see one joint here, another joint is there. So therefore two joints are used, and this may add to the flexibility of the whole system. Now where are these Hughes joints used or universal joints used? They are used mainly whenever we want some correction because of some inevitable manufacturing defects, or maybe because of vibrations. For example, in automobiles, when we want to transfer the power from gearbox to the back axle. It may be used when we give motion to adjustable shafts, for example multiple spindle drilling machine. It may be used even when we want to give power to a movable part, that could be used for example in the knee of the milling machine. So there are few various uses of the universal joints. Now we are going to look at some of the problems or the maybe the kinematics and strength of U joint. Now let me explain this with the help of this diagram. What you see here is the joint, and this is a very simplified view of this joint. This is the one shaft, which is, let us say, driving shaft, and this is the driven shaft. Now here this shaft, suppose we denote this name x, this is x axis, this is y axis, and this one is z axis. Now the another shaft, now here this pin makes an angle gamma with the x axis. Now this shaft is, or this line is on the xy plane. So therefore this angle is gamma, and definitely this also makes 90 degree with the, or yes, this always makes 90 degree with the with this pin. So therefore if you analyze it little bit carefully, then what you see is that this one, that is whenever you give a rotation here, so if it rotates by angle theta, let us say, then this vector, if I write down, this is x, y and z. So this vector, it rotates by, when it rotates, then this vector and both this one z. So this rotates by, so this pin, this particular pin rotates by angle theta. And now look at the other shaft. That shaft, this pin makes an angle here. So now you can find out this vector, which is a bar prime. Now originally the other vector was here b. Now after rotations, that is rotate by angle, if the driving shaft is rotated by angle phi, then this rotates, this goes to a new position b prime. Now you can find out a prime and b prime. Now that must be in terms of those angles phi and theta and gamma. Now you know that a prime, these are vector quantities, so a prime dot b prime is 0, that is the pins are at 90 degree apart. Now if you use these conditions, you get one relationship between theta, phi and gamma. Now where gamma is the angle made by the two axes, the two shafts, the accurate angle made between the two shafts. Okay, now you have this relationship. I am not going to derive this, but I ask all of you to have a look into this. Go whenever you have some time, just try to derive this. It is not that difficult. Now when we differentiate once, so if you make d dt differentiate of this entire expressions f theta phi gamma equal to 0, you get this following relationship. you get this relationship, that is theta dot is equal to cosine gamma divided by 1 minus sine square gamma cosine square phi and phi dot. So, this is the relationship between theta dot, which is the angular velocity of the driven shaft, and so let me write down, this is omega 2 and divided by omega 1 will be equal to cosine gamma and 1 minus sine square gamma cosine square phi. And again, if omega 1, that is the angular velocity of the driving shaft, is constant, then phi is nothing but omega 1 t. So, now you see this, the angular velocity of the driven shaft is now time varying. So, here we have this difficulty that although the the angular velocity of the driving shaft is constant, the angular velocity of the driven shaft is now changing with time. Now, let us look at the maximum and minimum values of that. Now, omega 2 maximum, by that is this will have maximum value when maximum occurs, when this denominator is minimum, that is this part is maximum, and that can occur when phi cosine phi is so the maximum value of it will be sine square phi, right. So, therefore, we have cosine phi cosine gamma divided by 1 minus sine square gamma. Again, if you write 1 minus sine square gamma to be cosine gamma, so this is nothing but 1 by cosine gamma. And then, so this is the maximum value. What about the minimum value? The minimum value will be when this one is maximum, and that can be only 1. So, this is cosine gamma. So, therefore, it varies from 1 by cosine gamma to cosine gamma, right. So, if gamma is say for the maximum limit 45 degree, then this varies from root 2 to 1 by root 2. So, this is there is a high fluctuations between the angular velocity. The relative change in the angular velocity can be written this way. So, relative change, that is omega 2 minus omega 2 max minus omega 2 mean divided by omega 1, this is the maximum change, and that you can prove to be cosine 1 by cosine gamma minus cosine gamma, which you can do a little trigonometric manipulations, and you get this is sine gamma times tangent gamma. So, one thing is clear, that if gamma is 0, then this becomes 0. So, for a perfectly aligned shaft, you get the same speed as that of the whatever you get the same speed that of the driving shaft. But if gamma is variable, then or non-zero, then you get some value of this. So, this is quite important, because we get a what is known as the variable velocity, variable speed, and with variable speed comes the variable bending moment, and that is also very much detrimental. So, now we see that one problem with the universal joint is that it leads to non-uniform angular velocity of the driving shaft. Now, how to take care of that? If you can use two such pairs, see here and there. So, there are two universal joints. Now, here the thing is that they must be parallel, these two are parallel shafts, and these two are in the same plane. That is, whenever that happens, then we can say, we can see that the angular velocity of the driving shaft will be equal to angular velocity of the driven shaft. So, by combining two universal joints we can get uniform velocity. There are other mechanisms also, or other kinds of universal joints also, which use a single universal joint, but it can have uniform velocity. So those are called synchronous universal joint. So there are few kinds, you can have a look at them in some good reference book, but those are used in automobiles, mainly in Soviet Russia. Now there is another problem which I am going to talk right now here, that is you see that now if this is the pin, now here one shaft is aligned that way, another shaft is aligned a little skewed. Then if you give a constant torque here T, then this part, one part can get, okay, if you can divide, that is you can have some component T1 and some component T2. So what happens? Then this T1 is responsible for turning of the shaft, whereas what happens for this T2? This T2 induces some bending moment. So if you look at the shaft, this shaft 2, then what you see that there is one T1 and there is another T2, and this T2 is nothing but the bending moment. So you will have to have some bearing here, and this bearing gets stressed and it leads to even fluctuating stress, and that may lead to failure. So these are the problems with the universal joint. Well, nevertheless, these are very popular joints, popular types of couplings in order to couple very heavy equipments, and these are in use. So this is all about the universal joint. Now we look at another kind of joint, another kind of coupling, which is known as gear or tooth coupling. Here you see this part. So again the flexible member is the gear. I shall explain how, but this part, let us see the diagram. This is the shaft 1 and this is another shaft 2, and this is connected by means of this sleeve. Okay, there are two sleeves here and there. So you see these are the parts of the sleeves, and these sleeves have thread, that is gear teeth, on the external surface. Again there is another shell which there are a couple of shells which are flanged together, as you see here, and this shells has the internal gear teeth. So therefore here the gear teeth match, as you can see here. So now this gear teeth can lead to some amount of flexibility. How? We know that there exists some backlash in the gear teeth. So because of the kinematic or the manufacturing defects, there may be backlash, and purposefully here some backlash is kept. So whenever there is some angular misalignment, then that backlash can take care of that misalignment. So this is one way it can take care angular misalignment, or maybe sometimes also the parallel offset misalignment. When there is axial movement, then of course it is very easy to see that one gear tooth can slide above the other tooth very easily, because there is lubrications there. So therefore it can take some amount of axial movement. So therefore this is very much useful. And what are the advantages of this kind of gear or tooth coupling? One is that it can have a very large capacity, right? The torque capacity is very large. Secondly, the speed may be very high, the gear may rotate at a large speed. And third, and which is very important, that is it is very easy to manufacture a gear. So the productivity is very large for the gear coupling. Therefore it has got wide acceptance amongst the industrial applications. But few things which we want to say here. For example, what you see here is a what you see here is again the gear coupling, but here the gear is spar gear, that is straight tooth gear, whereas here in this case the gear is now, you see this gear is has some other kind of teeth. So in one case we have this kind of spar gear, so this is the one tooth of the gear. So this is here what you see in the left figure. In the right figure you see this is relatively bent to a spherical surface, and you see this is somewhat bent, and this is known as crowned gear. This is crowned gear. So it again gives a little bit of flexibility to the overall system. Now this is something about the gear or tooth coupling. Now let us come to another coupling which is known as chain coupling. Here you see chains are used. So there are two shafts, shaft 1 and shaft 2, and again it is connected by two flanges, but there are sprockets there. What you see is these are the sprockets, and on sprockets we have this chain. Now chains are very flexible, as all of you know, therefore it leads to some it gives some flexibility to the coupling arrangement. So this is very accepted couplings, and there are large number of manufacturers for this chain coupling. Here what you see is again the photograph of a chain coupling. Here the usual chains are used, but there are double rows of chains. What you see here in this diagram, again the similar kind of chain, but now it is made of nylon. So this is nylon type chain coupling. Why it is used? It definitely, as you might have guessed by now, that it leads to some damping of the coupling. So it provides some damping arrangements as well. So these are some kind of chain coupling. Now again the next thing is the elastomeric pin coupling. Now here we first come across this term elastomeric coupling. Here what we do, we use elastomers, that is mainly the rubber material. We use elastomers. The most useful is the rubber, because it has a large storage capacity of load, that is it can take a large stress, and of course it's nowadays it is easy to manufacture and prepare. Now let us look at the salient features. What you see here is, this is again one shaft, this is the shaft 2, this is shaft 1, and again there are two flange coupling. Now this is very much similar to flange coupling, but unlike the other flange coupling which we have studied earlier, this has inherent asymmetry. So this part is not symmetric, so this is not symmetric as that. Now this is connected by bolts. Now here we have this elastomers. Now the elastomers may be a ring type, there is a small ring, or that may be a bush type, that is sometimes we have this kind of elastomer, this is a bush which is wound around the part of this bolt here, and then it provides some flexibility. Now when you want to design that, then definitely what is most important part is that bolt. Now this bolt design for the flange coupling we have seen already, but here the difference is that here for example I draw the part of this bolt, on top of it this elastomer, and again the load comes on this elastomer. Here comes the load, right, and that comes from the bearing pressure on the elastomer. Now you see this part, that is, which is subjected to both bending and the shear force. Now you see that there will be shear stress, in the bolt, as well as there will be bending stress. You see, if you can draw the bending moment diagram, you can have some kind of bending moment diagram which is something like this. So it has some bending stress here, and there will be the shear stress. So you have to calculate both the bending stress and shear stress, and therefrom you calculate tau sigma, and then you calculate either sigma prime is sigma square plus 3 tau square. If you use the von Mises theory of failure, or if you want to use the maximum shear stress, then maximum shear stress will be tau max will be equal to sigma by 2 square plus tau square, and either way you can check for the safety or the strength of the bolt, or you can design the bolt if you want. Now another way of looking at the stress is that of the bush. Here the bush, as you see, is subjected to, or the elastomer is subjected to bearing pressure, right, and this bearing pressure you can calculate, and the procedure is very similar to calculating the bearing pressure in the bolt in the flange coupling. So we are not going to discuss this. Now this is again a modification of the flange coupling, where we have used some kind of flexibility into it. Now this is about the elastomeric pin coupling. Now let us see the types of elastomers used in coupling. So there are various kinds of elastomers which are used as a member of coupling, and these elastomers, they are used either in shear or in compressions, but compression is the most favored only because that there is no need of bonding. You can imagine if you want to shear a rubber, then you will have to bond between two surfaces, whereas this bonding is unnecessary if you use the compressive stress. Now here what you see here, there are again there are two cases where a number of elastomers are used, as you see in the first row, and there may be a case where a single elastomer is used, which you see in the other rows. So this is the case where number of elastomers are used, and this is again working principle is compressions. So this is the part of shaft, one shaft, and this is the part of the other shaft, and they are connected by means of those compressive elastomers. Again this is the case, this looks like a trapezoid, where here it looks very much like a circle. So now again this is compressions. What you see here is again compression, you get compression from here, compression from there, but here you get both shear and compressions. It is subjected here, so you see that you can get compressive stress as well as the shear may occur along this plane. Here you get, in this figure you get compression as well as bending. Now because the force is acted here, force is applied there, so this bending might take place, that is it may deflect this way and that leads to bending. In this case this is a single member. Now this is subjected to compressions. In two shafts, each of the shafts you will get this kind of sprockets, okay, which when work they lead to compressive stress inside this member. So this is very much useful and it is used as a rubber sprocket member. This again has a complicated motions. Here this part, this is compressed and this is compressed. Similarly here the entire is this way along the clockwise direction. Here one part is in clockwise direction and another the anti-clockwise. Here of course there is a torsion, what you see here, there is a torsion. So if this is the elastomer, then it is subjected to torsion. Similarly here this is subjected to torsion. If this is connected to one shaft, this is connected to other shaft, when it rotates then you see a large torsional stress or torsional is developed, so shear stress develops, as well as in addition to pure torsion it also withstands some of shear. Here you see both the effect of torsion as well as shear. So when this is one shaft, this is other shaft, so whenever this way it moves in this way, then of course you get a large shear stress in this region. Similarly here, so these are the few cases where or these are the few types of elastomers which are used in coupling. Now if you want to know more about the elastomeric couplings, then you should read some book. We are not going to speak on the elastomer anymore. Now let us come to another kind of coupling which is known as metallic spring coupling. Here what you see is the two shafts and this is connected by coupling. Here there are two flanges and these flanges, there are two hubs here, what you see, two protrusions something like this, and there are slots cut over here. On the top of the slot we use the springs as you see here. So there are springs and these springs they look like so this is one part, this is another part. Similarly here there is one part, there is another part. So now if you look at the spring, then this is one side of the spring, these are the two parts as I say here this way. Now whenever there is a shock, then it can take care of the shock. This gives sufficient flexibility and this is very much used. This is sometimes called the Falk coupling, but this is metallic spring couplings. There are other kind of couplings, metallic couplings which use the disc or diaphragm. Now again if you want to know more about this disc or diaphragm coupling, please look at some good reference book. Now what we have known now few types of flexible coupling. The first kind is the kinematic flexibility, that is flexibility with the kinematic members, and we used Oldham coupling. We used we studied universal joint. Again we studied what is known as the gear or teeth coupling, and also chain drives. And in the flexible members we have used the elastomeric coupling. Elastomeric coupling we have only studied the pin type elastomeric coupling or sometimes pin bush coupling, and then I have shown you some types of elastomers which are used. Then lastly we have studied something about the metallic spring coupling. Now these are the broad overview of different kinds of flexible coupling. Let us look now at some dynamic considerations of the flexible coupling. Here when we design some flexible coupling, we will have to take care of few things. One is the stiffness of the coupling, and stiffness is just like when you talk of the stiffness of a spring, it is that if you have a spring, then if you elongate and elongate by a distance x, if you elongate by a distance x, then you measure the force, then you get this kind of curve, and the slope is known as the stiffness. So the stiffness is given f kx. Now then the second point is the damping of the coupling. Now whenever there is a motion is involved, then it must damp out, and those two are very much essential because the flexible couplings should also absorb some of the shock load. For example, take for example the case when we have reversal of drive, okay, in two-way drive, then there may be backlash, and because of backlash there may be sudden shock on the drive system, and we have to take this shock of the absorb the shock in the coupling itself, and we should not allow it to be transmitted, because if it is allowed to be transmitted, then the torsional vibration may take place, and that may lead to large fatigue stress, and which may lead to the ultimately lead to the failure of the member. So the stiffness as damping are very important thing. You see, sometimes when we have this kind of this diagram, then the stiffness, if it is linear stiffness, this diagram looks like this. So if you elongate, then it falls on this line, but if it is non-linear, that may sometimes happen, that if it is non-linear, then it may be something like this. Then when there is a damping present, then whenever you give excitations to it, then it traverses one loop per cycle, which is known as the hysteresis loop. Okay, this area of this hysteresis loop will be governing what is the damping inside it. Now if the linear spring is used and linear damping is used, then what you get, that if you find out the percentage of the load transmitted, so this is the percentage of transmitted load, transmitted torque or so, then with damping you get this kind of distributions. That is, if the natural frequency of excitations, that is excited force, is almost equal to the natural frequency, we get a large transfer. But if you use the damping high, then of course this peak gets down. If you use the non-linearity, then you get this kind of relationship. So you see, using the non-linear, we can reduce this maximum limit to a large extent. And the last point what we must know is the balancing of coupling. That is very important, and you must know that in a dynamic rotating system we always have to balance the machines. So these are the various points of the flexible coupling which we must consider. So that is all from today, and thank you very much. Lecture number 22, and the topic is design of riveted joints. Now in the last few lectures you were taught how to design one non-permanent joint. Non-permanent in the sense that the joints are such that any time they could be dismantled or disassembled if the requirement arises. So, these are the non-permanent type joints. There is another kind of joint which is known as the permanent fasteners or permanent joints. So, let us come to the types of permanent fasteners. Again, the permanent fasteners are those fasteners where the components can be disassembled only by damaging those components. So, here these are permanent joints. Now, again the components are held by two methods. They may be held by mechanical force, that is we give a large mechanical force such that they are held together. There are two examples. One is the riveted joint, which will be the subject matter of today's lecture. The second is the press fitted or interference fitted joint. This is again will be taught in somewhat details later afterwards, but here the purpose of the joint is that we press one part into the other and make a joint a permanent joint. The components could be held together by molecular force. There may be few situations, that is we talk of welded joints, we may talk of the soldered joints, and we talk of glued joints or using the adhesives. So, these are very important joints and will be discussed later on. So, now we start discussing on the riveted joints. Now, let us come to the basic geometry and the types of rivets. We must know what is a riveted joint, how does a rivet look like, and so on. So, let us see. A rivet, it looks like the following. So, this is the